For decades, quantum technology, well, it's felt tantalizingly close, but also kind of locked away, right? In these huge, pristine lab setups. Almost mythical.
Absolutely.
Yeah.
Giant optical tables, complex equipment, felt a million miles away from, mass production.
But what if that whole picture is changing, like
Hmm.
fundamentally? Today on the Deep Dive, we're looking at something that sounds straight out of sci-fi. A quantum light factory.
It really does.
And not some giant building, but crammed onto a tiny silicon chip, just 1 millimeter square.
Yeah, the sources you shared are fascinating. We're going to unpack this quantum light source factory on a chip. It's a really pivotal advancement.
Okay, so our mission today,
Yeah.
let's get into this breakthrough. Why is it such a big deal? What does it mean for, well, everything? Computing, communication, sensing. And here's the kicker right at the start. This isn't just another cool lab demo.
Yeah.
It's apparently the world's first electronic-photonic quantum system built in a commercial foundry.
Exactly. Using a standard 45 nanometer CMOS process.
45 nanometer CMOS. That's not bleeding edge. That's established tech.
Right, and that's the huge initial spark. It signals this fundamental shift in how you even build quantum hardware.
So it's not just science anymore.
Precisely. It tells you immediately this isn't just about proving a quantum effect in a perfect custom lab. It's about making quantum hardware that's, industrializable,
Yeah.
mass-producible, reliable.
Okay, so this tiny 1 millimeter square chip, it really is a factory.
In essence, yes. It functions as a quantum light source factory.
And what's rolling off the production line?
It's pumping out stable, reliable streams of what the sources call correlated photon pairs.
Correlated photon pairs. Okay, break that down for someone listening. What does that mean?
So imagine two photons, particles of light, that are created together. They're linked, intrinsically connected.
Linked out.
In a quantum way.
Mm-hmm.
If you measure something about one photon, say its polarization, you instantly know the polarization of the other one, no matter how far apart they are.
Ah, the spooky action at a distance thing. Entanglement.
Sometimes it is entanglement, or more generally, quantum correlation. And these linked photons, they're absolutely vital resources, kind of the building blocks for a whole bunch of quantum technologies.
Like quantum computers or maybe those unhackable communication networks.
Exactly. Quantum computing, quantum key distribution for secure comms. Yeah.
So the chip makes the key ingredient, but you said earlier, making these things used to be a nightmare.
Oh, absolutely. That's the huge problem this chip solves. Generating quantum light, especially these correlated pairs, traditionally needed these incredibly fragile, complex, large-scale lab setups.
Right, you picture scientists constantly tweaking mirrors on an optical table covered in black cloth.
Pretty much. Constant, delicate adjustments. This chip takes quantum systems out of that bespoke, temperamental lab environment and puts them onto robust, mass-producible silicon.
That's a massive leap.
It is. The sources call it a small step, but an important one, because it proves you can build repeatable, controllable quantum systems using standard commercial semiconductor foundries.
So it's really that shift you mentioned, from quantum science to quantum engineering.
Exactly. The focus shifts. It's not just, can we see this weird quantum effect? It's, can we make it reliable? Can we manufacture it consistently? Does it meet industrial standards? That's a whole different ballgame.
Reliability, manufacturability. That sounds way more practical.
It's a fundamental change in mindset, really, moving from curiosity-driven research to market-driven development. Suddenly you're thinking about quality control, supply chains, things scientists in a pure research lab might not prioritize.
Okay, so this leap from the fragile lab to something potentially industrial. How? How did they shrink it down and make it stable? That brings us to the core, right? How does the factory work?
Right. Inside the silicon micro world, the heart of the innovation is something called a micro-ring resonator.
Micro-in-ring resonator.
Sounds tiny.
Unbelievably tiny. The sources say no bigger than a fingernail, but actually they're much, much smaller. Think smaller than the thickness of a human hair. Tiny loops etched into the silicon.
Okay, tiny loops, what do they do? It's pretty elegant. You shine a pump laser light into these little circular channels. Inside, the light undergoes a process called spontaneous four-wave mixing, SFWM.
Spontaneous four-wave mixing, okay.
Yeah, it's a nonlinear optical effect. Basically, the intense laser light interacts with the silicon in the ring in such a way that it spontaneously creates new pairs of photons, those correlated pairs we need.
So the ring itself helps generate the quantum light.
Exactly. SFWM is actually a well-established way to generate quantum light states. The micro-ring just makes it happen very efficiently in a tiny space.
Sounds efficient, but you also mentioned earlier labs being fragile. Are these rings delicate too?
Ah, yes. The sources talk about this being a blessing and a curse.
How so?
Well, the blessing is their extreme sensitivity. That's why they're so efficient and compact. A little bit of laser light in, a lot of correlated photons out.
Okay, and the curse.
The curse is that same sensitivity. It makes the whole process incredibly susceptible to tiny changes in the environment, like minute temperature fluctuations, tiny vibrations,
Right.
even microscopic imperfections from manufacturing.
So like trying to do surgery while someone's bumping the table.
That's a great analogy. That level of precision is needed. And this inherent fragility, this sensitivity, is precisely why they needed the sophisticated control systems built right onto the chip.
Okay, so if these rings are that sensitive, how on earth do you keep them stable? Especially if you have, what, 12 of them working at once on this chip?
It's a huge engineering challenge, absolutely. And this is where the real genius of this specific chip comes in. They integrated a feedback system directly onto the chip that actively stabilizes these quantum light sources.
A feedback system, like a thermostat.
Sort of, yeah. You can think of it like a miniaturized lab assistant built right in. It never sleeps.
Okay, how does this mini assistant work?
So each microring has a tiny photodiode next to it. This little sensor non-invasively monitors the ring's performance. Is it aligned perfectly with the laser? Is it operating at the peak resonance?
It's watching the light.
Exactly. And if it detects any deviation, if that surgical table gets nudged, even slightly integrated control circuits instantly send a signal.
A signal to what?
To miniature heaters, tiny heating elements built right next to the microrings. These heaters make incredibly precise, tiny adjustments to the ring's temperature.
Ah, so they nudge it back into the perfect operating state.
Precisely. In real time, we're talking microseconds. It tunes the ring back to its sweet spot.
Wow. So this real-time stabilization of a quantum process,
Yeah.
it's not just neat, it's essential for scaling up, right?
It's absolutely critical. The sources call it a critical step towards scalable quantum systems.
Right.
It gets rid of the need for bulky external monitoring and control equipment.
But it lets you run multiple sources side by side, like the 12 on this chip.
Yes, without them interfering with each other. Each one has its own little stabilization system. It transforms this temperamental lab curiosity into something much more like a robust, predictable component.
The engineering must have been immense, getting the electronics, the photonics, the quantum part all working together on one chip.
Monumental. Co-designing the electronics and the quantum optics, pushing the boundaries of photonic design, but doing it all within the strict rules, the constraints of a commercial CMOS manufacturing process. That's the real tightrope walk.
Okay, let's pull on that thread. CMOS manufacturing. You said it's the unsung hero here. Remind us, what is CMOS?
CMOS, complementary metal oxide semiconductor. It's basically the bedrock technology of all modern electronics.
Like the chips in my phone, my computer?
Exactly, everything. It's the standard, mature, high-volume process for making integrated circuits. It's all about efficiency, low power, incredible density.
And making this quantum chip using a standard 45 nanometer CMOS process, why is that detail the game changer?
Because it lets quantum technology effectively piggyback on all that existing infrastructure. Decades of investment, refinement, massive factories.
So you don't need to build completely new exotic quantum foundries.
Not for this kind of device. You can leverage the existing, mature, incredibly high-volume commercial semiconductor foundries. That drastically cuts manufacturing costs and complexity.
That sounds huge.
It is. One source draws this powerful parallel. Remember the Intel 4004 microprocessor?
Vaguely the first one.
Yeah, back in the 70s. It basically kicked off the era of mass-produced classical computing, the CMOS quantum chip. It could be seen as marking the start of industrialized quantum hardware in a similar way.
Using a 45 millimeter process helps there too, right?
Yeah.
It's mature, well understood.
Absolutely. It's not some experimental bleeding edge node that's difficult to yield. It's reliable, which is key for actually manufacturing things at scale.
And I saw mentions of collaboration with big names.
Yeah.
Global Foundry's a major chip maker. And AIHardware, they do optical stuff for AI, right?
That's right. AIHardware is known for optical interconnects, basically using light to move data super fast, essentially relevant for scaling up AI hardware.
So quantum chips can now share production lines with, like, everyday electronics and AI chips.
Essentially, yes. And that synergy is profound. It massively de-risks investing in quantum hardware because you're not building everything from scratch. You slot into existing pipelines.
Faster development, too, I guess.
Yeah.
Sharing knowledge between quantum and AI hardware teams.
Definitely. Shared manufacturing expertise, shared technological advancements, it speeds everything up. And the core message here is building and stabilizing these complex quantum photonic systems entirely within a CMOS chip isn't just convenient. It's becoming an essential requirement if you actually want to scale quantum systems up.
Okay, so it sounds like this really unlocks mass production and scalability, being able to build, stabilize, and just replicate these quantum light sources on silicon.
Using traditional silicon manufacturing, yes, it fundamentally shifts the paradigm. It moves quantum tech beyond these one-off heroic lab experiments.
Right.
And into something that can actually be scaled up. You can imagine building large-scale quantum systems from many, many of these chips working together.
And that link to AI and optical interconnects, you mentioned IR Labs. Didn't NVIDIA's CEO, Jensen Huang, also talk about microrings?
He did. He explicitly identified microring resonators, the very same core component in this quantum chip, as being crucial for scaling AI hardware in the future for things like optical I/O.
Wow. So the same tiny structure is key for both next-gen AI and quantum tech.
It seems so. This convergence means quantum and AI hardware could potentially share very similar silicon platforms. Imagine the cross-pollination, the innovation that could foster.
Mind-bending. Okay, let's get practical. What are the real-world benefits? Size, cost, reliability.
Well, the size difference is stark.
Yeah.
What used to need literally an entire lab bench cluttered with equipment now fits onto a tiny piece of silicon on a wafer. You eliminate all that large external equipment, the specialized environmental controls, the constant manual tweaking. Huge footprint reduction.
And cost.
Yeah.
Using standard CMOS must help there.
Hugely. While the sources don't give exact dollar figures, the implication is clear. Substantial cost reduction. It's a much more cost-effective and monolithic solution compared to building those bespoke lab setups piece by piece.
And reliability. That built-in stabilization system must make a difference.
Absolutely. Predictable behavior, even if the environment fluctuates a bit, that's massive. It's the transition from something exotic and temperamental to something potentially industrial. That signals real commercial viability down the line.
But it's not completely solved, right? Quantum stuff is still notoriously sensitive.
No, it's definitely not solved entirely. It's still a continuous challenge. As the sources emphasize, tiny shifts in temperature, imperceptible manufacturing imperfections, they can still wreck a quantum system.
So the stabilization helps, but doesn't eliminate the underlying sensitivity.
Exactly. The integrated feedback directly tackles that vulnerability. It turns the curse of sensitivity into a driver for innovation. How do we build ever smarter, more robust on-chip control? It's about making it resiliently small, not just small.
And we keep coming back to this idea of different fields working together. Electronics, photonics, quantum measurement.
Yeah.
Domains that don't usually talk to each other.
It really stands out in the source material, doesn't it? That this success was as much organizational and cultural as it was technical. A heroic effort requiring tight coordination.
Can you paint a picture? What does that actually mean, getting these different experts to mesh?
Well, imagine quantum physicists used to thinking about ideal states and probabilities, suddenly needing to understand the nitty-gritty of CMOS design rules from electrical engineers worried about voltage drops and heat maps.
Right.
Or photonic engineers obsessing over waveguide dimensions and losses. They speak different languages, scientifically, different priorities. There would have been steep learning curves, debates, probably some arguments.
Probably.
But the fact they pulled it off, integrated these disparate fields onto one platform, shows how crucial breaking down those silos is for this kind of advanced technology.
Which brings up a good point. Silicon is great because of CMOS, but is it the only material people are looking at for quantum light sources?
That's an excellent question. No, silicon isn't the only game in town. There's a whole landscape of materials being explored.
Why look elsewhere if silicon and CMOS are working so well now?
Because while silicon is the king of manufacturing maturity, it does have limitations, especially optically. For instance, silicon itself isn't great at generating light efficiently. It has an indirect band gap, which is a physics way of saying it prefers making heat over light when you run current through it.
Okay, so what are the alternatives?
Well, there's silicon nitride. It has lower optical losses than silicon, meaning light travels through it more easily, and it's less sensitive to temperature changes. That's attractive.
Makes sense.
Then you have the 30V semiconductors. Think gallium arsenide, indium phosphide.
Sounds exotic.
They are a bit compared to silicon, but they have direct band gaps, making them fantastic for emitting light efficiently. Lasers, LEDs, they're often made from these. But the downside is much higher cost and very few large-scale foundries compared to silicon's CMOS.
Okay, others.
Lithium niobate is another interesting one. It's great for manipulating light at very high speeds, ultra-fast modulation, and has strong nonlinear properties, good for things like SFWM. But again, fabrication can be complex.
And I think I saw diamond mentioned.
Yes, diamond. Specifically, defects in diamond, like nitrogen vacancy centers. They can act as really good single photon emitters, which is crucial for some quantum applications and potentially for quantum memory. But integrating diamond smoothly with other photonics and getting it to emit light at the right wavelengths for fiber optics, still challenging.
So it sounds like this tension,
Yeah.
the universal material that does everything perfectly versus maybe combining different materials.
Exactly. That's the core strategic question.
Yeah.
Is there one wonder material, or is the future about hybrid integration?
Hybrid integration, like gluing different bits together.
Sort of, but much more sophisticated. Think like chiplets in classical computing. You might use a silicon base for the control electronics and maybe some waveguides because CMOS is so good at that.
Yep.
But then you precisely place a tiny 3V laser source on top for efficient light generation, or integrate a small piece of diamond for a quantum memory function. You combine the best properties of different materials on one platform.
Heterogeneous integration, they call it.
That's the term, yes. Heterogeneous or hybrid integration. It's likely where the field is heading for many advanced applications. But for now, and likely for the near future when it comes to mass production and cost effectiveness, silicon's maturity is just dominant. Its well-established CMOS processes and foundries make it the most practical and economically viable solution, even if other materials might have slightly better quantum physical properties on paper.
Manufacturability trumps perfection sometimes.
In the real world, absolutely. Cost and scale matter enormously.
Okay, let's zoom out again. Big picture. We have this potentially mass-producible quantum light source on a chip. What does this unlock? Applications. Let's start with quantum computing.
For quantum computing, reliable photon pair production like this is fundamental. You need potentially millions of high-quality physical qubits. This kind of chip is a step towards generating those qubits efficiently and integrating the control systems needed.
So helping to build the core processor, essentially.
Yeah.
Miniaturizing things.
Exactly. Making future quantum computers more compact, maybe more energy efficient, and ultimately more powerful by enabling scale.
Okay, what about quantum communication? Secure networks.
Yeah. The chip's ability to reliably churn out streams of correlated photon pairs makes it a perfect building block for things like quantum key distribution, QKD.
That's the one where eavesdropping inherently disturbs the signal.
That's the idea.
Yeah.
You use these correlated or entangled photons to create encryption keys that are theoretically impossible to crack without revealing the eavesdropper. This chip could make the hardware for QKD systems much more practical and deployable.
And quantum sensing.
Right. The sources mentioned this could open doors there, too. Imagine compact, robust, ultra-sensitive quantum sensors based on these chips. Sensors that could measure magnetic fields, gravity, maybe even biological processes with precision far beyond classical devices.
So computing, communication, sensing. It's a foundational piece.
It really is. It represents a significant step on that long, decades-long road from quantum concept to quantum reality. It provides these fundamental building blocks made in a way that suggests mass production is feasible.
And you see the momentum, right? People moving from universities to companies like Sequantum, IR Labs, Google X.
Definitely. That flow of top academic talent into industry is a huge indicator that the field is maturing, getting serious about commercialization.
And the synergy with AI hardware just adds fuel to that fire.
It absolutely does. It creates this powerful feedback loop, accelerating progress on both fronts. It's a really exciting convergence to watch.
Okay, so let's try and wrap this up. To recap, this tiny 1 millimeter square quantum light source factory on a silicon chip. It feels like a truly transformative moment. It's changing how quantum hardware is made, moving it from the lab to the foundry by integrating the quantum light sources with the electronic controls needed to stabilize them, all using standard CMOS.
Yeah, tackling that historical fragility and the massive scaling challenge head-on, and crucially making it commercially plausible by leveraging existing, proven manufacturing, de-risking the whole endeavor.
So thinking about that bigger picture, how this quantum breakthrough is deliberately piggybacking on classical chip infrastructure and even finding synergy with AI hardware.
Mm.
Makes you wonder, doesn't it?
Who's that?
Well, what does it tell us about how big technological leaps happen now? Is the future of innovation less about completely separate revolutionary paradigms popping up out of nowhere?
And more about.
And maybe more about the clever integration, ingeniously layering these cutting-edge quantum capabilities onto the incredibly robust foundations we've already built with classical computing and AI. Maybe progress looks more like smart integration than complete replacement.
That's a fascinating thought. Is the next revolution built on top of the last one, rather than sweeping it away entirely? Definitely something for you, our listeners, to ponder.